And the sort of general theme for the seminar was ancient solutions to geometric flows. And my goal today is really just to give a sort of 30,000-foot overview of the topic. I'm going to focus mainly on, almost entirely on mean curvature flow, because I'm not really an expert in, for example, Ricci flow, but I'll just focus on mean curvature flow and try to sort of discuss a little bit analogies with other settings. And I'll also try and point out some topics which might be good, some suggestions for other people to talk about later on if they so desire. Also, sorry to the experts, because this is probably going to be fairly pedestrian, at least the first sort of 3/4 of the talk. And it won't be until towards the end that we see some more contemporary results. Anyway, with all that in mind, let's start off at a very classical result, the Leoville Theorem. So just recall that the Leoville Theorem, I'm sure you all know it, and you all probably know at least 2 or 3 different proofs of it. It says that a bounded entire harmonic function must be constant. I'll just present here, because I couldn't resist, the proof of Nelson, famous proof of the theorem. So Nelson says that, well, what we do is we take 2 points. We want to show that the function takes the same value at both of those points. And what you do is you take a circle of radius r about one of the points, and a circle, hopefully I can get the same radius about, it's not quite a circle, but you get the point. And then what you do is you take that radius larger and larger, and if you zoom out at the same time, what you're going to see is these circles are going to overlap, except for an arbitrarily small portion of their areas. But then, since the functions are bounded, their averages over the average of the function over each of the 2 balls has to be arbitrarily close. But of course, by the mean value property, the average over a ball is the value at the center. And so taking the limit gives you the result. So that's just a classical, obviously classical theorem that you all know. And the moral of the story here is that diffusion smooths out, and absolute diffusion smooths out absolutely. So here you're allowing diffusion to act over an infinitely large distance, and being able to act over a very large distance means that everything gets completely smoothed out. Of course, like all morals, this is of only limited value, because without this boundedness hypothesis, we get many additional examples. Here's one. So under certain conditions, yes, the moral holds true, but without those restrictions, other things can happen. And of course, it's worth mentioning that the theorem holds assuming only a one-sided bound, and in fact, that bound can be replaced by a growth rate, sublinear growth rate. So that's the sort of the model version of most of the results I'm going to mention today. An interesting, since we're doing geometric analysis here, an interesting extension is of course to the geometric setting. So Leoville's theorem holds in ambient manifolds or complete manifolds of non-negative Ricci curvature. This was proved by, well, it follows from the gradient estimates of Cheng and Yao. So those are stated here as follows. So basically, the gradient of the logarithm of a positive harmonic function over a ball of radius r over 2 is controlled by 1 over r. So here the Cn is a constant that just depends on the dimension, and K is a lower bound, negative lower bound for the sectional curvature. So you can see here if K is can be taken to be 0, then we can just take r to infinity, and we get that the logarithm is constant, and the claim follows. So this proof, I guess, is more interesting for us because it illustrates some more general techniques. it's proved by multiplying with cutoff functions and applying the maximum principle. So it's sort of a cutoff function maximum principle argument. And these kind of arguments have been used a lot since. For example, the Lee-Yao-Hamilton differential Harnack inequalities are also maximum principle type arguments. Okay, so that's the sort of classical Leoville theorem and the less classical geometric analog. Another result of a very similar nature is the well-known theorem of Bernstein, which states that entire minimal graphs are flat. So if you, this should be in R3. So entire minimal graphs in R3 are planar. So that's a result of a very similar nature. Let me just briefly remind you of the proof. So the idea there is to show that the total curvature is 0, which then implies that the curvature is pointwise 0. And of course, that implies that it has to be flat. This uses the minimizing property of minimal graphs, the stability inequality. So since they're minimizing, they're stable. You can exploit the stability inequality and the so-called logarithmic cutoff trick. And that's where the two-dimensional hypothesis comes in here. So this is a nice illustration of our model. We've got diffusion acting over all of space, and then we get that our solution has to be flat. Of course, as you probably know, Bernstein's problem gets a lot more interesting when you go up in dimension. You need to use different techniques because this logarithmic cutoff trick doesn't work. And then following an idea of Fleming, you can prove Bernstein's theorem so long as you can rule out the existence of stable minimal cones. And this can be done, it was done by Simons in low dimensions. However, there are counterexamples in higher dimensions. So again, our model holds, but only up to a point. Okay, so we want to talk about geometric flows. So let's start with the heat equation. So I recall that, of course, the heat equation is just so this is the heat equation for, whoops. So take a function on say Euclidean space times an interval, and this gives us the heat equation. In this setting, diffusion is sort of acting only in one direction in time. So diffusion will improve things, but only as you move forward in time. And so here we should expect that although there are many solutions which exist on large forward times intervals, we shouldn't expect there to be many solutions which exist on large backwards time intervals. Because if the solution has existed for a very long time in the past, then diffusion has been smoothing it out for a very long time. So we should expect the same kind of rigidity phenomena. And of course, we do observe that. And here's the theorem of Souple and Zhang. Probably mispronouncing both of those names. In any case, the theorem states that if we do give ourselves an ancient solution to the heat equation on Rn, and we suppose that we have some growth rate. So here, so recall that Leoville's theorem held for positive harmonic functions. Here we also need an upper growth rate of this form. Or if we don't assume that it's positive, but we assume this stronger growth rate, then we again find that the solution has to be constant. And let me just briefly mention that the proof is again, as for the Leoville theorem, it's based on gradient estimates. And here the analog of those gradient estimates are as follows, and I hope I copied that down correctly. So here we have the gradient of the logarithm of the solution is again bounded by, so bounded now in a parabolic ball by 1 over r plus a lower bound for the Ricci curvature, which I haven't mentioned yet. Okay, so you can take that to be 0 in Euclidean space, but we also get this additional term, 1 plus logarithm supremum of u over u. And again, this is obtained by constructing appropriate cutoff functions and the maximum principal argument. So here, this is the gradient estimate that holds in Riemannian manifolds with Ricci curvature bounded from below by K. So this result also extends to that setting. Okay. So, but as I mentioned, here we had these additional hypotheses. So for Leoville's theorem for harmonic functions, we needed no upper bound, but here we have one. And in fact, this is necessary. So why is this necessary? Well, here are a couple of examples. So in the first case, we can consider the traveling wave solution, e to the lambda x1 plus lambda squared t. So this is a positive solution which only just violates this upper bound. And we've also got the sort of stationary affine functions, of course, violate this second one. Okay? So the second condition says we want a sublinear growth rate. So in that sense, this result is essentially sharp. Okay, just want to quickly mention that you can also obtain similar results. Instead of using gradient estimates, you can exploit the modulus of continuity estimates, which were developed in Julie's thesis. And you can, but these require appropriate boundary conditions. So that basically replaces the gradient estimate arguments. You can do these modulus of continuity arguments. And just quickly, the idea there is that the modulus of continuity of a solution to the heat equation, which is defined as follows. So it's the maximal difference between the function values with fixed distance between the domain values. And the idea is that the modulus of continuity it turns out to be a subsolution to the one-dimensional heat equation with boundary conditions induced by those of the heat equation problem. Okay, so that's the heat equation. So the next setting I want to mention is that of semilinear heat equations, because that might come up again later. Okay, so we consider the following semilinear heat equation. Oops. Okay, so now we have this reaction term of order P, and we consider the subcritical exponents here, P between 1 and n plus 2 over n minus 2. And then there's this, oops. Okay, so we want to look at ancient solutions to this semilinear heat equation. So because of this reaction term, solutions to this semilinear equation actually blow up in finite time. And in fact, after rescaling, these blow-up solutions, these blow-ups are modeled by ancient solutions. So ancient solutions sort of arise naturally there. And we have the following theorem of Merle and Zard. So they prove that if you do have a positive ancient solution, and again, if you have some growth rate, then you get a Leoville type result. So either the solution is the zero solution, or it's this special self-similar solution. Okay. And the proof of this result is based on the analysis of a Lyapunov function. So it's sort of a very dynamical systems type proof. But again, the moral continues to hold true. We've got ancient solution to a certain parabolic equation. Under mild growth conditions, we get a classification. So that brings me to the mean curvature flow. So I know not everybody here is an expert in this area. So let me just take a little bit to introduce the mean curvature flow. So morally speaking, this can be thought of just as a heat equation for an immersion. So we have, so X is a one parameter family of immersed submanifolds, really, of Rn+1. And the mean curvature vector here, it's really a kind of Laplacian of the immersion. So it really can be thought of as the divergence of the derivative of the immersion. So you can think of it as a Laplacian. So here, this really looks quite a lot like the heat equation. It's not the same as the harmonic map heat flow, because here we're using the induced geometry. So this divergence uses the induced geometry, and that depends on time. So that's how it differs from, say, the harmonic map heat equation. But we can still think of this as being a heat equation for this family of submanifolds. Okay. There's another way of thinking of this equation, which sort of fits well with our analogs with Leoville type theorems. And that's as follows. So if we suppose that each of the hypersurfaces, each of these evolving hypersurfaces in the family, is mean convex and bounds a region omega, depending on t, then we can define this time of arrival function, u. So we can define it as exactly the time. So u of a point x in our ambient space is exactly the time at which the evolving front passes through that point. So we have a family of surfaces which sort of evolves and moves through space, and then since these fronts are mean convex and the flow is the mean curvature flow, they move only in one direction. So given each point in the interior, there exists a unique time at which the front passes through that point. So this is well defined, and then just by formally differentiating this relation here, just by replacing x by, say, the parameterization function and then differentiating this equation, you get you find that u satisfies this equation here. So you can also think of this sort of heat equation for our family of submanifolds as this degenerate elliptic equation for the time of arrival. So which can be quite useful in certain settings. And of course, just to remind us, we did assume that our time slices were mean convex and bound some region. Okay. So it's a lightning introduction of mean curvature flow. And of course, we want to talk about ancient solutions to geometric equations, geometric flows. So of course, we're going to be interested in ancient solutions. And again, those are just solutions which are defined on infinite backwards, half infinite backwards time intervals. Okay. But if we look at the time of arrival function, so if we have a mean convex embedded solution, then this is really the same as saying that the arrival time is a complete function. So this gives a sort of fairly exact analogy between the elliptic and parabolic Leoville type philosophy. So there's basically two reasons here that we should expect our ancient solutions to be quite rigid. One is as a sort of ancient solution to a parabolic equation, and the other is as a sort of complete solution to an elliptic equation.
What do you mean by complete here? Just minus a proper function or something, is that right?
Yes, exactly. Yeah. So ignoring what happens sort of forward in time, I guess, assuming that that forwards in time, the surface does close up. I'm just saying here that at the boundary of its domain, it goes to minus infinity. Okay. Thanks, mate. Okay. So these objects are obviously very interesting, just purely in terms of these rigidity properties, these Leoville type properties. But they also, very importantly, they also arise as singularity models for the flow. Indeed, let's suppose that we have a solution to mean curvature flow, which is developing a singularity forward in time. So we have a sequence of space-time points, so a sequence of times, sequence of points in the corresponding time slice, and we suppose that the norm of the second fundamental form, so that the curvature is going to infinity as j goes to infinity. Then what we do is we just consider this parabolic rescaling. So we rescale in space by lambda j, we rescale in time by lambda the minus j. What we end up with is another solution to the flow for each j. This parabolic rescaling produces a further solution to the flow. And if the sequence does converge, for example, if this is the maximum of the curvature, then under the rescaling, we get something with bounded curvature and we get convergence. And by the way this is defined, the limit will have to be an ancient solution. So because we've rescaled time by lambda, this should be a lambda sub j, I'm sorry. So because of the way we've rescaled, the new flow will be defined for all, sorry, this should be for all backwards times. Okay. So okay, I've been a bit vague here. I should have been a bit more careful. So in general, we won't expect to exist for all forward times, but certainly for all backwards times. And moreover, a very fundamental and important result, a deep result of Huysken's sinistrari, says that if the underlying solution here is compact and mean convex, then the blow-up limit actually has to be, so this limit, if it exists, will actually have to be convex. So that's why I've written here that convex ancient solutions model mean convex mean curvature flows. So the convex ones are also of particular importance here. And I guess here I'm just saying that again. So if we can understand ancient solutions, then by this kind of blow-up procedure, we can understand the local geometry at singularities, which is of course very important. I should probably say here that most of this slide also holds good for many, many geometric flow equations, and in particular, an analog of all of this holds for Ricci flow. And hopefully Tim will be able to talk about that. Okay, so let's see if we can talk about some examples. So the prototypical examples are the shrinking spheres. So that's just a family of spheres with appropriate radii. So that satisfies mean curvature flow. This is obviously defined for all t less than 0. So we get an ancient solution, and multiplying by flat factors gives us new solutions. So we call these guys shrinking cylinders. And okay, so we have these examples, and let me just mention the following sort of basic theorem, which gives us a rigidity result for the shrinking spheres. And basically, so just very vaguely, roughly speaking, I'm not going to be too precise, but this is really a sort of a sequence of theorems which says that if we take a compact ancient solution and we assert fairly mild but sort of scaling invariant hypotheses, such as uniform curvature pinching, then the only solution is going to be the shrinking sphere. So as soon as you put some kind of mild but scaling invariant geometric condition onto the solution, it has to be the shrinking sphere. So this is very much in the vein of the Leoville type theorems. Okay. So let me mention here a whole bunch of further results. So this very basic theorem about rigidity of the shrinking sphere solution has many generalizations. So there's a nice theorem by Paul and Janelle Louis, which gives uniqueness of the analogues of the shrinking circles for a curve shortening flow on the sphere. So that's for ancient solutions to mean curvature flow on the 2-sphere, and maybe Paul can talk about that at some point. There's lots of results about, Paul with Mohammad Ivaki and Julian Scheuer have some results about fully nonlinear flows, so more general kinds of hypersurface flows for hypersurfaces of the sphere, and rigidity results there. Choi and Mantelidis have some uniqueness results, again for mean curvature flow on the sphere, as do Huska and Sinistrari. So that's for spherical ambient spaces. Lambert, Lotte, and Schulze have some results about Lagrangian mean curvature flow. These are some more results about fully nonlinear flows. There's some results about high codimension flows. This sort of covers all of the above. And there's another nice result of Sonnenberg, but I've forgotten exactly the statement. But in any case, there's many results there which sort of continue in this similar theme, rigidity of the shrinking sphere solution, but in more general and different contexts. Okay, so I won't talk about the proof of that, not today. Maybe somebody else would like to talk about that later on. Oh, and it's also worth mentioning, I probably could have had an equally long list under here about analogues of this result for the Ricci flow. So there are also results of this form, uniqueness of the shrinking sphere amongst ancient solutions for the Ricci flow. The most basic one, which I think was due to Brendler, Huska, and Sinistrari, is under a uniform pinching condition. So the analog holds there for Ricci flow as well. Okay, let me now just briefly discuss the sort of main tools and techniques which are involved here, which also emphasize the relationship between monotonicity formula and self-similar solutions. So the first tool, which is fundamental in most of this theory, is the monotonicity formula of Huska, which says if we look at this Gaussian density, if we take the Gaussian density and look at the corresponding area, then this is monotone under mean curvature flow, and in fact you get this nice right-hand side. And then you get a rigidity case as well. So not only is this monotone, it's strictly monotone unless this integral is 0 on some time slice, but this is the defining equation for a so-called self-shrinking solution. So a self-shrinking solution or a shrinking solution is something that evolves purely by homotheties in this way. And the integrand here is the defining. So this vanishes if and only if you're the time slice of one of these guys. Okay, so this Gaussian area is monotone, and in fact strictly monotone unless you're a shrinking solution. And the other important monotonicity formula that comes up here is the differential Harnack inequality of Hamilton. I might give a proof of this in the one-dimensional case next week. Maybe you could consider this one an exercise, the Gaussian area. This might be a nice exercise if you're a PhD student and looking for something to do during COVID. The general case of this one is a little bit harder. but as I said, I might give the proof for the curve shortening flow next week. But basically it says that if our flow is strictly convex, so our solution to mean curvature flow is strictly convex, then with respect to the gas map parameterization, this function, the square root of t times the mean curvature, is monotone, non-decreasing. So the gas map parameterization means that h at a point z, well, that that this is the value of h at the point whose normal is z. So you parameterize over the sphere, and the mean curvature at the point z is the mean curvature of the point on the submanifold whose outward pointing normal vector is z. So you parameterize by the normal directions. And you can do that by the hypothesis here that you're strictly convex. And of course you get a rigidity statement here again as well. So this inequality is strict unless you're actually an expanding solution. So this monotonicity is strict unless you're an expanding solution, which means that you evolve by positive homotopes. More interestingly for us, and for my talk next week, is if we assume, instead of looking at this time interval, we assume that we're an ancient solution, then we can prove something stronger. We can prove that the mean curvature itself is pointwise non-decreasing in time in the gas map parameterization. And indeed, again, we get a rigidity case. This will be a strict inequality unless our ancient solution is actually a translating solution. So this is, so hopefully again next week, in my talk next week, we're going to be using the monotonicity formula is going to be crucial, and the Harnack inequality for ancient solutions. So these work very well together for studying ancient solutions. Okay. Let me briefly talk about the shrinking solutions, and then I'll talk a little bit about the translating solutions, because these obviously give examples of ancient solutions. So obviously a shrinking solution is always an ancient solution. You can define this for all negative t. And a translating solution, that's a solution that just evolves by unit speed translation, or constant speed translation. So these are obviously examples of ancient solutions, and they're quite important examples. So let me mention first these particular examples. So if I take any pair of relatively prime integers p and q satisfying a certain condition, then there exists an ancient solution, a shrinking solution to curve shortening flow. That's the one-dimensional mean curvature flow with the following properties. The -1 slice has rotation index p, and it lies in an annulus about the origin and touches each boundary q times. So that this gives existence of a large class of these shrinking solutions for curve shortening flow. Of course, these kinds of curves can't be embedded. They look something like this spirograph curves. It's not a very good picture, but you get the point. And then there's, well, okay, maybe one more thing. It's worth also noting that the shrinking solutions are critical points of the Gaussian area. So as you might expect from the monotonicity formula. So you can also think of them as minimal surfaces with respect to the so-called Gaussian metric. And we have the following well-known theorem of Kolding, Minkowski, and Huisken, says that the shrinking cylinders, which we've already seen, and the Albrecht-Langer cylinders, which we've just defined or introduced, are the only examples you get if you assume that you have, so the only shrinking examples you get if you assume that you have mean convexity and finite Gaussian area. So that's another, again, that's another Leoville type result. So this tells us we can completely classify them under these mild natural conditions. Okay, let me just mention a few more examples. So without mean convexity, okay, there's a huge class of examples which are now known. Most of these are fairly recent constructions. But basically, people have constructed a lot of new examples once you remove mean convexity. On the other hand, so I don't want to talk about exactly these examples, but just note that there are many, many examples. On the other hand, we have this sort of Hopf-type theorem of Brendler, which says that the shrinking sphere is unique amongst compact embedded spheres in R3. So there's only one compact embedded shrinking sphere in R3, topological sphere, and that's the one we know. But not much else is known. So apart from this huge class of examples and this uniqueness result, not much else is known. There's this result of Mortimer and Wang, Shengwen Wang, which says that if you have genus 1, so if you're an embedded self-shrinking torus in R3, then, well, at least it has to be unknotted. But in fact, there's this conjecture that there's indeed only one. So there's still this sort of open question, I think it's probably a conjecture, that the genus 1 example constructed by Angenant, it's a rotational self-shrinking torus. It's embedded, it has genus 1. The conjecture is that it's the only compact embedded genus 1 example. So that would be, I guess, an analog of the Lawson conjecture. And this is very much open because it's not even known, as far as I know, whether it's unique under rotationally symmetric shrinking tori. So I think that's quite an interesting question. But that's all I'll say about shrinkers. So the other class of ancient solutions, which we mentioned, the other class of self-similar ones was the translating solutions. So sort of very basic theorem is if you look at the one-dimensional case. So the only examples in the plane are stationary lines. So if you take a stationary line, then this up to reparametrization, this translates parallel to itself up and down. So you can think of this as a translating solution because the image, of course, doesn't move under mean curvature flow. So you can think of it as a translator. But a less trivial example is the so-called Grim Reaper, which is pictured here. So here, this is just a curve which moves sideways with speed 1 under the flow. So that's very easy. That's just you just solve the corresponding ODE, but a very useful theorem. Okay, I want to talk about this next week. So I'll give the details, but let me just mention the result here. So let's see. So we've seen these soliton examples to curve shortening flow. We've seen the shrinking circles. We've seen those vertical lines or stationary lines and the Grim Reapers. So those are the only ancient solutions to the one-dimensional case that we've seen so far. But these are kind of trivial examples because they're either stationary or they're just self-similar examples. There's a quite famous non-trivial example called the Angenant oval that's defined by this equation. But let me just show you what it looks like. In fact, you might recognize it from the title page of this talk. So this is a non-trivial example because it clearly doesn't evolve by self-similar shrinking. It doesn't evolve by translation or expanding or rotating or anything like that. So this is what I'll call a non-trivial example. It's not self-similar, and it's also an ancient solution. So this is defined for all t less than 0. And this theorem, which I'll present some or all of the proof of next week, says that these examples are the only ones which are convex and compact. So the only convex, compact, ancient solutions to the one-dimensional mean curvature flow are these four: the stationary lines, shrinking circles, Angonite ovals, and grim reapers. Sorry, the only compact examples are the shrinking circles and the Angonite ovals. Okay, so that gives a complete classification of examples in the one-dimensional case under these two fairly natural conditions. So that's quite a nice result. It's a complete classification essentially. And again, the proof is based on the analysis of a certain Lyapunov functional, and this proof is actually closely related to the proof of the result I mentioned earlier about the semilinear heat equation. So the methods and techniques are very closely related between those two settings. And in fact, maybe Timothy will speak about this. Similar methods were also used by these same three authors in the two-dimensional gas curvature flow. So there's an analogous result holds for the two-dimensional, mean curvature, Ricci flow. Apologies. So the two-dimensional Ricci flow, ancient solutions admit a similar classification or an analogous classification, and I think the proof of all three of those results is closely related. Okay, in the last 5 minutes, maybe I'll just quickly mention one more thing. Yeah, I should have enough time. Okay. So let me mention a very powerful result, which is tremendously useful and perhaps also quite surprising, due to Shuja Wang. So if we take a mean convex ancient solution, embedded, say, then as we saw, we can define its time of arrival function, and we'll call the solution an ancient solution, or say a mean convex ancient solution entire, if its arrival time function is an entire function. So if it's defined over all of Rn plus 1. Then the result is as follows. It says that if we look at a convex ancient solution, so an ancient solution with convex time slices to mean curvature flow, which is not entire, necessarily lies in a stationary slab region. So a slab region is just the region between two parallel hyperplanes. So you cannot have ancient solutions which sweep out half spaces. They either sweep out all of ambient space or precisely the region between two parallel hyperplanes. So this is a very strong and important theorem. I guess I have time to give a quick sketch of the proof as I understand it. Although it's quite a technical theorem. This might also be a good topic to cover if somebody wishes to.
So the hypothesis here is that the hypersurfaces are compact, right? The fixed T is compact.
I'm not sure that's completely necessary.
Okay.
Yeah. So that's not. They should have bounded curvature if they're not compact. Mm-hmm. But I think that's enough. Yeah. So yeah, so either compact or complete with bounded curvature. Okay, and the first thing to note here is that using the monotonicity formula, if we do these rescalings, okay, so if we rescale by lambda and take lambda to 0, this is called the blowdown. So using the monotonicity formula, we always get a limit, and the limit is always a shrinking cylinder of this form. If k is not equal to n, or if k is equal to n, this will either be a hyperplane of multiplicity 1 or 2. So basically, we scale down and take lambda to infinity. But then, of course, if k is less than n, it sort of immediately follows that the solution is entire, because these shrinking cylinders are entire. So we're just left with the case that this blowdown is a hyperplane of multiplicity either 1 or 2. If the multiplicity is 1, the monotonicity formula tells us that the solution has to be a stationary hyperplane, because we can sort of do a blow up and get a hyperplane at some point, but then by the monotonicity formula, the Gaussian area is constant, and you can just see that you have to get a hyperplane of multiplicity 1 for all t. And so you're left with the case that you have a hyperplane of multiplicity 2. Okay, and then that's where really all the details are in this proof, which I'm not giving. But basically, if you do get a hyperplane of multiplicity 2 as a blowdown, that basically says that your solution is bounded between two planes whose distance grows less than the square root of t. And then all of the work is done in showing that, in fact, you can improve that to big O of 1. You can show that it lies between two fixed hyperplanes. And that argument relies on exploiting concavity properties of the arrival time, which is equivalent to the differential Harnack inequality. Okay. And that argument, I'm fairly sure, to answer Ben's question, does work in the non-compact time slice setting, as long as you assume that your time slices have bounded curvature, because you need to use the differential Harnack inequality.
Sorry, what's an example for that case?
Oh, so exactly this one. So
okay, sure.
Yeah, this guy, essentially you can just think of this guy, well, I'm going to call it jousting Grim Reapers. So you can just think of it as a Grim Reaper evolving in this direction and another one evolving in this direction, but they sort of join together in the middle. So it lies between two fixed planes. So when we do this scaling, this sort of long distance goes sort of like t. So this distance increases like t. This is bounded. So when you rescale, this bounded distance goes to 0. This t-like distance goes to infinity. Okay, good question. And of course, the other examples is the shrinking sphere here, which is, of course, sweeps out all of space. So, okay, that brings me, so let me just quickly maybe mention the topic of my talk for next week. Will be an extension of that previous theorem. Let me just put it up here. So with Theodora Borni and Giuseppe Tenaglia, we proved that if you remove the compactness hypothesis, the only additional examples you get are the stationary lines and the Grim Reapers. So the only convex ancient solutions to the curve shortening flow are the 4 that we've seen: shrinking circles, Ungenant ovals, stationary lines, and Grim Reapers. So I'll leave it there because I want to present that proof in more detail next week.